Think about the shape of a tree stump, not a mountain, a stump, because the moment you allow that substitution to sit, without immediately dismissing it, you cannot look at a flat-topped mesa quite the same way again. That is the thing I keep returning to, slowly, without wanting to, and now out loud. There is a shape that geology produces in abundance across this planet, and it is not scattered or random in its character. Flat top, steep, nearly vertical sides. A width that dramatically dwarfs its own height. You find it in Monument Valley. You find it rising from the Sahara. You find it on every inhabited continent. We call them mesas. We call them buttes. We have an entire vocabulary built around these formations, as though naming them thoroughly was equivalent to explaining them. The official explanation is erosion, resistant caprock on top, softer stone beneath. Millions of years of wind and water doing their slow, patient, completely documented work. And that explanation is not wrong, exactly. I want to be clear about that, because dismissing the mainstream account prematurely is the laziest move in any investigation. Erosion is real. Differential erosion is real. Geologists have mapped these formations with extraordinary precision, and the science behind caprock preservation is internally consistent and well evidenced. But here is the thing about an internally consistent explanation. It can be technically accurate about its mechanism while being completely silent about what it operates on. Erosion shapes things. It does not originate the underlying form. And the underlying form, that flat, wide, truncated cylinder, is worth examining entirely on its own terms. The question I keep landing on is this. What produced the form that erosion then acted upon? What was there before, hard enough at the top, vertical enough at the sides, and wide enough at the base to produce what we now walk past and photograph and call natural? That question is almost never asked. In the late Silurian and into the Devonian period, roughly 420 million years ago, something lived on this planet that does not fit comfortably into any of our existing biological categories. It is called Prototaxites. It grew to nearly 9 meters in height. It had no leaves, no bark, no branches in any recognizable sense. Scientists have debated for over a century what Prototaxites actually was. Early classifications called it a conifer, then a liverwort, then an alga. A 2007 study by C. Kevin Boyce and colleagues suggested fungal origin based on carbon isotope analysis. The debate is never fully closed. The organism defies every clean category we try to place it in. What is not debated is its scale. In the early Devonian, before recognizable forests existed, before anything we would call a tree had evolved, Prototaxites was the tallest living thing on land by a significant margin. It rose over a landscape of low-lying plants, the way a silo rises over a meadow. Singular, enormous, not quite anything. Now I want you to hold that image for a moment. A 9-meter organism, roughly pillar-shaped, wide at its base, standing alone on an open, largely barren landscape. Then I want you to look at a photograph of a butte in Monument Valley, and I want you to sit with what you notice before you decide what to call it. I am not telling you they are the same thing. I want to be precise about what I am actually doing here, which is noticing a shape that appears in the fossil record, and a shape that appears in the current geological landscape, and asking whether the relationship between those two occurrences has ever been seriously examined. The honest answer is that it has not, at least not directly. The Prototaxites literature is extensive, but focused almost entirely on classification. What was it, taxonomically? Not on what happened to it over geological time, or whether its fossilization patterns might correlate with surface topology. That question, as far as I can determine, has not been formally posed. Now move forward to the Carboniferous period, roughly 350 million years ago. The planet was covered in what we now call coal forests. Lepidodendron, a real, well-documented species with an extensive fossil record, grew to 50 meters in height, taller than a 15-story building, achieved without secondary wood growth or annual rings. These organisms, and I use the word loosely because Lepidodendron was not a tree in any modern sense, had enormous pillar-like trunks with distinctive diamond-patterned bark. When they fell and were buried under specific anaerobic conditions, they became coal. When something different happened, when silica-rich water infiltrated the tissue, they became stone. Perfectly. Molecule by molecule. What we know about Lepidodendron's structural biology makes the scaling argument more plausible, not less. The organism grew primarily through apical extension and did not branch significantly until near the end of its life. The trunk was a single, largely undivided column for most of its height. A silicified trunk of that architecture would produce precisely the form we are examining. This process is called silicification, and it is not controversial. The Petrified Forest National Park in Arizona exists because of it. Walk through it, and you will find logs with grain and cellular structure intact, turned entirely to quartz. The wood is gone, the shape remains. Every space the organic material occupied is now silicon dioxide. The petrified forest preserves logs up to approximately 60 meters long, and these are only fragments, sections of ancient organisms that broke apart before or during fossilization. We are not looking at complete specimens. We are looking at pieces, and the pieces alone are already the size of large structures. This is what I keep sitting with. If an organism the size of Lepidodendron, or something larger, something not yet classified, because we only recover fragments, were to undergo silicification at sufficient scale, what would the result look like from above? What would it look like from a distance, after millions of years of the surrounding landscape eroding away around it? I do not have a clean answer, but I notice that the question produces a shape in my mind that I recognize. Flat top, vertical sides, wider than it is tall. A form that resists erosion more aggressively than surrounding material because silicified biological tissue is in fact extraordinarily hard. Harder than most sedimentary rock by a significant margin. Silicon dioxide, quartz, has a Mohs hardness of 7. Sandstone, which makes up much of the material surrounding formations like those in Monument Valley, typically registers between 2 and 4 on the same scale. When material fossilizes into quartz and softer surrounding stone erodes away, the harder structure is left standing alone. That is uncontested geology. So here is what we have, using only documented and peer-reviewed science. Organisms of enormous size existed. Silicification preserves their exact structure in a material far harder than surrounding rock. Erosion removes softer material over millions of years. Resulting forms in documented fossil sites are tall, columnar, and frequently flat at the top. Each statement is individually unremarkable. Now consider the distribution. Petrified wood has been documented on every continent. Mesa-type formations exist on every continent. The overlap is not perfect, but it is significant enough that I would expect the comparison to appear as a formal research question in published literature. As far as I can determine, it does not exist in print. Consider the Roraima Tepui in Venezuela, more specifically. It rises approximately 2,800 meters above sea level, with nearly vertical sandstone walls and a flat summit that sits above the clouds. It is among the oldest geological formations on Earth, and the contrast in hardness between its walls and the surrounding, far more eroded landscape is pronounced enough to require its own explanation. The Drakensberg Range in South Africa contains flat-topped formations at altitude that have resisted erosion, while surrounding basalt has worn considerably. The Bungle Bungle Range in Australia, extraordinary beehive-shaped formations of striped sandstone, presents a variant of the same geometry. Extreme vertical containment of hard material, surrounded by a much more weathered landscape on every side. I want to pause here and name the most obvious counter-argument, because it deserves serious attention. The counter-argument is scale. Lepidodendron grew to 50 meters. Mesas, depending on which one you are examining, can be hundreds of meters wide and tall. The size difference is enormous, and I'm not going to pretend otherwise or quietly wave it away. But consider two things simultaneously. First, we are speaking of organisms from 350 million years ago, and we recover only fragments. We have no reliable way of knowing the upper bound of what existed. Second, Prototaxites was already operating at a scale biologists found nearly impossible to explain, and we have direct fossil evidence of that one. There is also the trajectory to consider. Prototaxites, 9 meters. Silurian. Lepidodendron, 50 meters. Carboniferous. The arc across those periods is one of dramatic biological scaling. There is no scientific principle requiring that trajectory to stop at 50 meters. We simply lack evidence of what came after, because the largest organisms may not have preserved in ways we recognize. Now I want to talk about Devil's Tower in Wyoming. It rises nearly 390 meters above the surrounding terrain. It is composed of igneous phonolite, officially explained as a volcanic intrusion. Magma forced upward through the earth, with softer surrounding sediment eroding over millions of years, leaving the harder igneous column standing alone. The formation has columns. Long, parallel, hexagonal columns running vertically from the base to the flat summit. They are real, well documented, and result from the way molten rock contracts as it cools. This is established igneous petrology. The columns themselves are not controversial. What I want to note is something adjacent to them, not about them. The hexagonal column structure appears in two separate contexts in nature. One is rapidly cooled igneous rock, the Giant's Causeway in Northern Ireland, or the columns of Devil's Tower. The other is the cross-sectional vascular tissue of large plant organisms. Both produce the same interlocking hexagonal arrangement through entirely different mechanisms. I am not claiming they are the same. I am noting that. Here is where I want to slow down and be genuinely careful. The columnar jointing at Devil's Tower is well explained by igneous cooling physics, and that explanation is supported by the mineral composition of the rock itself. I cannot honestly dispute that mechanism, and I do not intend to present it as an open question when it is not. What I can note is this. Phonolite, the rock of Devil's Tower, is not associated with biological fossilization. Silicified wood becomes quartz. Phonolite is something different. If Devil's Tower were the remnant of something biological, the preservation pathway would need to be unlike anything currently documented. I cannot explain that pathway, and I want to be honest about that. So why am I still sitting here? Because Devil's Tower is one among many formations combining extreme vertical height, a flat summit, regular columnar sides, and a hardness that allowed persistence while surrounding material eroded away. That combination is not common in pure igneous geology. It is, however, common in the structural profile of large ancient organisms. Let me look at the global pattern more broadly. In Morocco, Flat-topped formations rise from eroded plains. In Venezuela, the tepuis have sheer walls, flat summits, and surrounding lowlands worn by millions of years of tropical erosion. In Australia's Kimberley region, similar forms appear. The same shape across climates, across rock types, across continents, each arising independently. The official explanation handles this through planation surfaces, ancient flat landscapes preserved in uplifted terrain, eroded at their edges. It is a real concept and documented, but planation surfaces tend to be regional and interconnected, not isolated columns. The isolated tower, the lone butte, the single mesa requires a different explanation than a broad plateau. That distinction matters considerably. I have been asked, when I raise this line of thinking, what I am actually claiming. And the answer is that I am not claiming anything. I am noting a convergence of documented facts that produces a question no one is currently asking: whether some percentage of what we call geological formations may have begun as biological structures of extraordinary scale. The reason that question is never asked is institutional. Geology and biology are separate disciplines with different methodologies, journals, and professional vocabularies. A question requiring both to engage simultaneously does not fit the grant structures of either field, so it does not get asked. Not because anyone decided to suppress it, but because it falls cleanly between the disciplines. And that, I think, is how significant questions get lost. Not through coordinated suppression, not through any conspiracy requiring deliberate decisions about what you are allowed to know. Through the far more mundane mechanism of categorical disorganization. Questions that live between established fields have no institutional home. They do not need to be buried. They simply never get funded. This dynamic is not new. There are documented historical cases where questions spanning disciplinary boundaries went unasked for decades. Barry Marshall, who proved in the 1980s that stomach ulcers have a bacterial cause, worked at the junction of microbiology and gastroenterology, a space where no one had thought to look because neither field had reason to examine the other's domain. There are researchers who have touched adjacent ideas. Francis Halla, the French botanist, spent decades studying the architectural principles of large tropical trees and documented scaling behaviors, suggesting biological systems can maintain structural integrity at far greater sizes than we typically assume. His work is mainstream and well regarded. It is simply never connected to geological morphology. There is also what early European observers described when they arrived in landscapes later settled and normalized. Many accounts from the American Southwest describe formations that indigenous people did not treat as geological curiosities, but as something else entirely. Places with presence, with relational meaning requiring particular acknowledgement. That is not scientific evidence, but it is context worth noting. The Lakota call Devil's Tower, Mato Tipila, Bear Lodge, and regard it as sacred. The Kiowa and Crow have separate names and separate origin narratives, each treating it as something with a nature preceding geological time. I am not appropriating those interpretations. I am noting that independent cultures without contact converged on a non-geological understanding of the same structure. Now let me return to the coordination problem, because it matters. If there is something being missed here, and I remain genuinely uncertain, it would not require active suppression. It would only require that the existing institutional structures have no mechanism for asking the question. No mechanism, no funding, no journal. The silence organizes itself without anyone intending it. Think about what a formal investigation would actually require: expertise in igneous petrology, sedimentary geology, paleobotany, biological scaling theory, and isotopic chemistry assembled as a single research team. That team does not exist as a configured unit in any department I am aware of. The question cannot be formally asked within the existing structure, not forbidden, unconfigured. And this is where I want to be careful about my own conclusions. The most dangerous moment in any investigation is when evidence starts to feel like it is pointing. Pointing feels like understanding, but it is not the same as knowing. I have been in this territory long enough to distrust the sensation of approaching certainty before the work is complete. Let me give the mainstream account its strongest possible reading. Mesas form through erosion of horizontally layered sedimentary rock. Resistant caprock preserves the flat top, while softer material erodes beneath. Vertical walls result from the caprock preventing gradual slope formation. The timescales are well constrained. The shapes produced are predictable from the input conditions. It is genuinely a strong account. Where it becomes less comfortable is the caprock itself. Resistant caprock is identified primarily by its survival. Hard because it persisted. Persisted because it was hard. That is not entirely circular, but it leaves the origin of the hardness unexplored. What made certain deposits dramatically harder than everything surrounding them? The answer is typically mineralogical. That answer deserves careful attention. The hardest caprocks and mesa formations are frequently silicified. Silicon dioxide, quartz. The same mineral that replaces organic tissue during fossilization. Silicified caprocks are sometimes described in the literature as exhibiting secondary silicification, meaning silica introduced from an external source that infiltrated the existing material. The precise origin of that secondary silica is not always cleanly identified. I am not inventing this. Secondary silicification in sedimentary environments is a documented phenomenon. The source of the silica, hydrothermal fluids, groundwater, or other origins, is actively discussed in geological literature. What I am noting is that one possible source of large-scale silica introduction would be the in situ breakdown of a massive silicified organism. That source is not discussed. Someone will point out that compositional analyses of these formations reveal no biological signatures. This is true and important. But biological signatures, carbon isotope ratios, cellular microstructure, degrade over geological time. At 300 million years, organic markers become undetectable, even in confirmed biological samples. Absence of signature at that timescale is not equivalent to absence of biological origin. I should also acknowledge that silicification at mesa scale would require staggering quantities of silica-rich fluid over an enormous span of time. Computational morphology, comparing shape profiles across geological and biological datasets, is a developing field. The investigation is not impossible. It simply has not been started. That is a meaningfully different problem from impossibility. We named them, we studied them, we photographed them, and built viewing platforms at their edges. In all of that looking, the question of what they were before they were stone was answered once, quietly, and filed in a discipline that does not speak to the one next door. The question did not disappear, it simply stopped being a sign. The next time you see a flat-topped mountain on the horizon, I want you to notice the top. Not the base, not the walls, not the surrounding terrain. The top. And I want you to ask a simple question. Is what you are looking at the summit of a geological formation, or the crown of something that once grew toward the sky? Because those are different things. And after spending this much time with the question, I am not sure we have definitively established which one applies. The distinction may not matter for most purposes. The mesa is still a mesa, and you can photograph it and move on. But for understanding what this planet was before we arrived, the difference is everything. There is a version of Earth's history encoded in schools and national park placards. It is coherent and mostly true, and missing something. I do not know what. I do not have a replacement account ready, but I know the shape of the gap, and the shape of the gap is flat on top, steep on its sides, and harder than everything surrounding it.